So in the previous lecture, we were discussing row space, column space, and null space of a matrix. So as I told you in the previous lecture, null space, what is null space? Row space and a column space. In fact, these spaces are related to the matrices, particularly the coefficient matrix of the linear systems. For example, if we have any linear system, AX is equal to B, then this coefficient matrix, we need to discuss its the solution of the spaces related to the solutions of this linear system. So if we put this non-homogeneous linear system, if we convert it into a homogeneous linear system, then AX is equal to 0. Okay. Then the set of all solutions of this homogeneous linear system is basically called the null space of a matrix. So null space of this, you can say this matrix, coefficient matrix. So the null space is what? Is the set of all solutions of this homogeneous linear system. Okay, null space is the set of all solutions of the corresponding, you can say, corresponding homogeneous linear system. Homogeneous linear system. So first, we shall discuss the null space and its basis and dimension. Okay. Now, how to find the basis and dimension of the null space? Whatever matrix we are given, whatever matrix A we are given, if we want to find its null space, then we have to write a corresponding homogeneous linear system with the help of that coefficient, that matrix A. Then we solve it, and we can find the set of all possible solutions. Now then, there are two cases here. As we know that this linear system, homogeneous linear system, is always consistent. So it must have two possibilities. Either this homogeneous linear system has only one solution, which is a unique solution, which is a trivial solution, x equal to 0. In that case, this null space will contain only one vector. So there are two cases. Case one, unique solution, unique or trivial solution. In that case, x is equal to 0 is only solution of that corresponding linear system because, and when does this exist, the unique solution, the null trivial solution? If the coefficient matrix is invertible, means if A inverse exists, or you can say that A is non-singular matrix. And it can only be verified or checked that A is non-singular only if A is a square matrix. Okay, so A must be a square matrix. A must be a square matrix first, then we can check whether it is invertible or not, or it is non-singular or not. Now, case two is, in that case, the solution set contains only, the solution set of this homogeneous linear system contains only one element, which is the 0. And it is the subspace of what? How do we know कि ये किसकी subspace है? Anyone? If the order of this matrix A is some square matrix A n cross n, then this space, which is the solution space, null space, you can say that it is a null space, null of A. This is how we denote it, null space of A. It is it contains only the 0 vector, and it must be the subset of R, subspace of Rn. So if this matrix is singular, the coefficient matrix is singular, or if A is singular, or A is a rectangular matrix. In that case, you cannot have only one solution. You must have infinite many solutions for this coefficient matrix. In that case, the null space will contain infinite many elements and vectors. Let's discuss this thing, which is the more general. If the order of A is m cross n, means it has m rows and n columns. Then if we want to write the corresponding homogeneous linear system, then A times X must be equal to 0. Now, if the order of A is m cross n, then what should be the order of n? Obviously, it should be n cross 1. Okay. In that case, this homogeneous linear system, the solutions of this homogeneous linear system will be the vectors which has order n cross 1. So the null space in this case will be the subset or subspace of what? Subspace of Rn, this one. Okay, so remember this, null space is always the subspace of this n, which is the number of columns in that matrix A. So remember this thing. So in this case, the null space will have infinite many solutions, and the vectors in null space are basically n-dimensional. Okay, it means that null space is a subspace of Rn. Let's have an example of this thing. For example, if we, this one, maybe, this thing, let me take some homogeneous linear system example. If you have any question from here, you can ask me. There's no example. Yes. Yes, here it is. No, I can't. I don't have example of this thing. Let me. You can take any. For example, this one. Maybe we have a homogeneous linear system x1 plus 3x2 minus 2x3 plus 2x5 equal to 0, and 2x1 plus 6x2 minus 5x3 minus 2x4 plus 4x5 minus 3x6 equal to 0, and then 5x3 plus 10x4 plus 15x6 equal to 0, and then 2x1 plus 6x2 plus 8x4 plus 4x5 plus 18x6. So this is a given homogeneous linear system. Okay. So we can solve this system by converting it into the reduced echelon form. If we try to convert it into reduced echelon form, so you write the corresponding augmented matrix, and you try to write a solution. So as the matrix is rectangular matrix, obviously the solution of this homogeneous linear system would definitely involve free variables. And after introducing free variables, I can write solution directly x1, x2, x3, x4, x5, and x6. Okay, and the solution is r times -3, 1, 0, 0, 0, 0, plus s times -4, 0, -2, 1, 0, 0, plus t times -2, 0, 0, 0, 1, 0. So this is the solution set of this homogeneous linear system. Kindly verify it yourself. But the solution set will be of this form. Okay, if there might be some mistake in it. So now you can see that where R, S, and T, they belongs to R. Now, if these R, S, T are free variables, if we change the values of R, S, and T from R, how many solutions do we have? Infinite many solutions. So the null space, basically null space of A will contain the vectors of this form. And now you can see that the coefficient matrix here, A, is of order what? It has 4 equations and 6 columns. So it is 4 cross 6. And you can see that the solution vectors are basically what they are of 6 dimension. So null space must be the subset of R power, subspace of R power 6. So null space contains all the vectors which are solutions of this homogeneous linear system. And the null space is basically the subspace of R power 6. Now, all possible solutions are basically the linear combinations of these 3 vectors, this vector, and this vector. These 3 vectors, they are generating null space. How they are generating? Because if we change the value of R, S, and T, we get the multiple of this vector, multiple of this vector, and multiple of this vector. And set of all linear combinations of these 3 vectors, in fact, that space forms or contains infinite many vectors, and that space forms the null space of A. Now, if we say that these 3 vectors generate this null space, then what does it mean? The null space of A is generated by or spanned by, it is spanned by these 3 vectors. If we call it this, we call it V1 vector, we call it V2 vector, and we call it V3 vector. So the span of null space is what? It contains v1 vector, v2 vector, and v3 vector. Okay. So these three vectors are basically generating null space. If you have any question, you can ask me. If you have any kind of confusion, you can ask me. Okay. Now, if these three vectors span null space of A, and when does a set of vector is a basis of some vector space? If I say that this set is also linearly independent and this set is spanning or generating null space of A, then I can say that null space of A has a basis set, these three vectors. These three vectors will form the basis of a null space. Now, we know that these three vectors generate null space of A. If we can further verify that these three vectors are linearly independent, then this set, the set of v1, v2, v3 vectors, they will form the basis of a null space. Okay. I hope you can check whether these three vectors are linearly independent or not. Now, further, we need to check we need to verify or check. Verify v1, v2, and v3. This set is linearly independent. I hope you can do it yourself. Do it yourself. Okay. I know that these three vectors are linearly independent. So if these three vectors are linearly independent, as well as they are generating null space of A, then these three vectors forms the basis of a null space. So I can say that this null space, the basis of a null space, basis of nulls of A is what? It is v1 vector, v2 vector, and v3 vector. Okay. So the basis of null space contains v1, v2, v3. If this is the basis set of a null space, then what would be the dimension of null space? Anyone? I told you what is dimension in the previous lecture. Anyone tell me?
So 3.
Why is it 3?
जो आपने elements के बारे में कहा था, अपने elements नहीं मुझे पता कितने हैं.
How many elements are there in null space which generate in the basis of null space?
3 लगा है मुझे तो.
लग रहा है क्या? मतलब नजर नहीं आ रहा आपको?
सर पता नहीं.
हाँ?
सर 6/1 होएगा क्या?
ये देखें, three vectors है ना basis set में. So what is the dimension of any vector space? It is basically the number of elements in the basis set of that space. Okay. How many elements are there in the basis set? 3 elements. So the dimension of this null space is 3. Okay. So the dimension of this null space is dimension of null space of A is what? It is 3.
सर फिर जो आपने पिछले पार्ट में पिछले बोर्ड पे आपने बात की थी m by n की और सर आपने कहा था कि n का आपने वो was that the dimension or was that आपने कि vector space as in किस vector space से belong करता है that is R of n.
Yes.
उस बात पे confuse हो रहा.
I told you कि अगर आपके पास A के कॉलम्स n हैं तो जो null space के vectors होंगे वो n dimensional होंगे. Means null space will be a subspace of a vector space Rn. हमने ये नहीं कहा था कि इसकी डायमेंशन क्या है. Rn की डायमेंशन n है, but we don't. But this is the subspace, is a subset of Rn. We don't know what is the dimension of null space of A still. Okay? अभी तक हमने ये नहीं कहा कि इसकी डायमेंशन क्या होगी. Dimension is the set of vectors in the basis set of that space. पहले हमने basis set find करना है कि basis set क्या है इसका null space का. The number of elements in that basis set will be the dimension of that null space. I hope you
Sure,
get
sir.
it. If you have any question,
Thank you, sir.
any other? There's a question in the chat window. Let me see it. What is the timing of the quiz? Every time you ask me, but I hope everyone know at what time quiz starts normally. So this is all about the null space of a matrix A. Okay, the null space of a matrix A. So in order to find, let me summarize all these things. Null space of a matrix A, if we want to find it, we have to write the corresponding homogeneous linear system. The first thing, we write the corresponding homogeneous linear system. We solve it, okay? We solve it, then there are two cases. If its solution contains only the unique vector or the trivial vector, then the null space contains only the one vector. It is still a vector space, which is a subspace of Rn, because a set containing 0 identity element of this vector space is always a subspace of this thing. I told you this thing already when we discussed the subspaces and vector spaces. Now the case 2 is if A is singular or a rectangular matrix, then we cannot check whether A is invertible or not. Okay. Then in that case, we write the corresponding homogeneous linear system and solve it. Okay, as we did here in this case. This is a homogeneous linear system. We need to find its null space. What we do, we write the corresponding augmented matrix and we solve it. After solving it, we can have a solution of this kind, which will definitely have free variables in it. Okay. Now, after looking at the solution, we can say that the null space is generating by these vectors, this one, and this one, and this one. We call it V1, V2, V3. So V1, V2, V3 generate null space of A. Okay, we can write that these three vectors, span of these three vectors is basically the null space of A. If these three vectors, they are linearly independent, but which usually are, but you have to verify it. If they are linearly independent, then these vectors form the basis of a null space. Now, the dimension of the null space of any vector space, not only null space, dimension of any vector space is the number of elements in the basis set of that space. So how many elements are there? 3 elements. So the basis, so the dimension of null space is 3. This is how we compute the null space. Now, if I write this basis of a null space, what does it mean? How this can help us with regard to the linear systems, homogeneous linear systems. Okay, if someone asks me that these 3 vectors are the basis of the null space of this homogeneous linear system, then what do I understand from here? I would immediately know that these 3 vectors, they span the solution set of this homogeneous linear system. It means the solution of this homogeneous linear system is some kind of linear combination of these 3 vectors. I can immediately write any particular solution or any required solution which I want with the help of these 3 vectors for this homogeneous linear system. Okay. I hope you get it. If you have any question, if you have any confusion, you can ask me. So if you don't have any questions, let me go now to the row space. Row and column space, we'll discuss them together because they are connected with each other. Now we are going to discuss these row spaces and column spaces. As I told you, what is a row space? Row space is basically row space is a space generated by or spanned by, you can say, spanned by all rows of the matrix A. Okay. What we are discussing, null space of a matrix A, row space of a matrix A, and column space of a matrix A. Okay. But the row space is a space generated by rows of the matrix A. For example, if we have a matrix, maybe 2, 3, -1, 0, and 4, 5. Okay, this is a matrix. How many rows are there? This is the first row, row vector. This is the second row vector, and this is the third row vector. Okay. Now the row space of A is basically row space of A is what? It is the space generated by spanned by R1, R2, R3. Okay. The set of all possible linear combinations of R1 and R2, R3. The set of all possible linear combination of these three rows will be basically a row space of A. There is a question in the chat window. I hope it should not be related to the quiz. Okay, Syed Kabir, sir, if we have another vector in the solution of vector X, and that vector is a vector of constant, mean it's not the multiple of this, then will the force vector still spanning null space? If you have homogeneous linear system, then you cannot have a constant vector here. Kindly turn off your mics. Whose mic is on? Syed Kabir, you talk to me. Turn on your mic and talk to me. Okay, if you have a homogeneous linear system, then you cannot have a constant vector here. Okay. If you have a non-homogeneous linear system, then you can have a constant vector here. Okay. In the case of homogeneous linear systems, you cannot have a vector without some parameter, because you have zeros on the right hand side. So if there are non-zeros on the right hand side, then you can have some constant vector here. Okay. I hope you understand. We have observed this thing in solution of non-homogeneous linear systems, that we can have a constant vector which is independent of some parameter here, but only in the case of non-homogeneous linear systems. In case of homogeneous linear system, we cannot have a constant vector without some parameter here. Okay. Okay, I hope you get it. What was I talking about? Yes. Now you look at here is at this matrix, the set of all linear combinations which we write by using these row vectors R1, R2, R3, then that set will be a row space of A. Now you can see from here that how many entries are there in each row? How many entries? There are 2 entries. So it means every row vector R1 belongs to what? Belongs to R2, because R1 has 2 vectors. It's a row vector. So it must belong to R2. Similarly, R2 and R3, they belongs to R2. So now, if we see that this row space of A, it should be the subspace of what? Anyone?
R2.
Yes. So the row space is always, is here in particular. Row space of A must be the subspace of R2 because every row vector has two dimensions, two components. So it must contain all the set of these kind of vectors. They must belong to R2. So the all set which are spanned by these three vectors, they must be subspace of R2. Okay. Means if you have an order of a matrix, you see that order of a matrix is what? 3 rows, 2 columns. So there are 3 rows, but every row has 2 components. Okay. There are 3 rows, but every row has 2 components. So the row space must be a subspace of R2. Remember this. This dimension always confused. So you have to take care of these things. Now, what is the column space? I told you. On the same lines, the column space is a space generated by the columns of the matrix A. Now, the column space denoted by col of A. Okay, is the set of all vectors. Yeah, आप कह लें, is the space generated by, that would be better, is the space generated or spanned by the columns of A. Okay. Now here let me write it again. So the column space of A must be a space spanned by the columns. If we call it this the column 1 and column 2, then we have column 1 and column 2. There are 2 columns. We call C1 to be the first column and C2 second column. Now, every column, there are 2 columns in this matrix, and every column has a dimension 3. Okay, has 3 components. You can say this. Okay, every column has 3 components. Means C1 belongs to what? R3, and C2 belongs to R3. Okay. So this column space contains all the vectors having 3 components. So it must be the subspace of R3, obviously. So there are 2 columns. There are 2 columns, but every column has 3 components. So the column space must be the subspace of R cube. Remember this. Don't confuse with these dimensions. If the matrix is a square matrix, then they are subspaces of the same space as the order of a matrix of that square matrix. I hope you get it. If you have any question in this, you can ask me. Now,
sir.
जी बेटा.
सर मैं ask a question. सर इसमें जो हम लोगों ने रो स्पेस फाइंड की है, तो इसकी जो डायमेंशन है वो 3 है ना हमारे पास, कि मतलब वो सबसेट तो R2 का है, बट इसमें क्योंकि 3 एलिमेंट्स है R1, R2 एंड R3, तो जो रो स्पेस है A की, इसकी डायमेंशन 3 है, और इसी तरह जो कॉलम है उसकी डायमेंशन 2 होगी.
अभी तक हमने ये नहीं प्रूव किया कि ये इसका बेसिस सेट है. अभी हमने ये कहा है कि R1, R2 is spanning row space. Did I tell you that this is a basis set of row space? No. So the dimension of any vector space is the number of elements in the basis set, not the spanning set. So it is not the dimension of row space. We have to prove whether these three row vectors are linearly independent. If we can prove, then we can say that this set is a basis set of the row space of A, and then the number of elements in the basis set is basically the dimension of row space. I hope you get it.
Yes, sir.
Still,
Thank you.
still we are not sure that this is a basis set. It is possible that the basis set contains only two row vectors. It is possible. Then the dimension of the row space would be 2, not 3. These three vectors are spanning only the row space, not the basis set of row space. So you have to be careful while defining the dimensions in basis and spanning set. Okay, there is a difference between spanning set and basis set. Yes, जी बेटा.
सर अगर लीनियरली डिपेंडेंट हो जाते हैं तो फिर हम बेसिस किस तरह डिफाइन करेंगे, कर सकते हैं हम इस केस में?
If I can prove, or if you can prove that R1 and R2 and R3 are linearly independent, then this set will become the basis set of row space of A. If this set becomes a basis set, then we can say that there are 3 elements in the basis set, so the dimension of a row space of A must be 3.
सर अगर डिपेंडेंट हो फिर क्या करेंगे?
डिपेंडेंट होंगे तो फिर हम देखेंगे कि क्या करना है. Still, we haven't talked about it. Okay. Now we are going to talk about the bases of the row space and bases of the column space, how to find them. Okay. So let's discuss now how to find the basis and dimension of vectors of row space and column space. But before that, we need to discuss a couple of results, couple of theorems, which will help us finding row space, the basis set of a row space and basis set of a column space. We need to discuss a couple of theorems. And those theorems are basically theorem. Elementary row operations do not change the row space of a matrix. Okay. Row operations do not change the row space of a matrix. What does it mean? It means if we have a row space of a matrix which is generated by the rows of a particular matrix, and we try to reduce that matrix A into echelon form or reduced echelon form. Okay. Echelon form or reduced echelon form, then that basically that matrix will have a same row space as the original matrix has. Okay. So in continuation to this theorem, there are 2 more results. Let me write those results first, and then we'll discuss all these results and theorems. These theorems will help us in defining row space and column space and finding basis of row space and column space. If A and B are row equivalent matrices, then First, given column of vectors, column vectors, a given set of column vectors of A is linearly independent if and only if the corresponding column vectors of B are linearly independent. If and only if the corresponding column vectors of B are linearly independent. Now, what does it mean? If we have two equivalent matrices, I hope you know, I hope you remember what are equivalent matrices. Equivalent matrices are basically if A is some matrix and we apply some elementary row operations, and we obtain another matrix B after applying a single elementary row operation or a series of elementary row operations. In order to reduce this matrix into reduced echelon form, we apply normally the elementary row operation. Then we say that these two matrices are equivalent. I told you at the start of this course what are equivalent matrices. So two matrices are equivalent if they are row equivalent. It means if we apply any number of row operations on A set and we obtain B set, then they are row equivalent. And two linear systems are also basically row equivalent if we apply elementary row operations on the augmented matrix. I told you this thing. So
सर रो इक्विवेलेंस आपका ये मतलब है कि उसका मैट्रिक्स सॉरी उसका डिटरमिनेंट सेम रहेगा. हमने पढ़ा था कि उसे चेंज इन डिटरमिनेंट. सही है सर. नेवर माइंड. थैंक यू.
Okay. We are in fact talking about with the reference of linear systems. Okay. So a given set of column vectors of A is linearly independent if and only if corresponding column vectors of B are linearly independent. So हमारे पास A मैट्रिक्स है, उसको उस पे हमने elementary row operations apply किए. We get another matrix B which is in the echelon form or reduced echelon form. These two matrices are row equivalent. Okay. Now, how this thing will help us in finding dimensions and basis of a column space and row space, we'll discuss in the next result. But the second part of this theorem is very important as well. A given set of column vectors of A form a basis for the column space of A if and only if the corresponding column vectors of B forms a basis for the column space of B. So a given set, let me write it for you, the given set of column vectors of A forms a basis for the column space, forms a basis for the column space of A if and only if the corresponding columns of B corresponding, what did I write here? Corresponding columns of B forms a basis for column space of B. Okay. So what does it mean? If we have two matrices which are equivalent, okay, then the column vectors, the column vectors of A will be linearly independent if and only if the column vectors of B are linearly independent. Okay. The second result is also very important. A given set of column vectors of A forms a basis for the column space of A if and only if the corresponding columns of that equivalent matrix B, which has been already reduced into echelon or reduced echelon form, if the columns of that matrix B, column space, has what? Forms a basis for the column space of B. So these two results, after these two results, we still do not know how to find the basis of the column space of any matrix. The next result will clearly tell us how to find the basis of the column space. Okay. The next result is basically is a key in finding the basis of column space and row space. So if a matrix R, if a matrix R or any other recurrent matrix, if a matrix R, this is a matrix R, not a real number, is in row echelon form, then the row vectors with the leading ones, the leading ones, the non-zero row vector, you can say, forms a basis for row space of R. And the column vectors with leading ones of the row vectors form a basis for column space of R. Okay. Now this result has basically removed our confusion how to find the basis of a row space and column space of any matrix. Now, in the previous results, we can say that every elementary row operations do not change the row space of a matrix. Means if we have two matrices A and B, B is basically the reduced echelon form matrix of A after applying series of the elementary row operations. If we obtain B, if A and B are two row equivalent matrices, then a given set of column vectors of A is linearly independent if and only if the corresponding column vectors of B are linearly independent. ठीक है? अब ये रिजल्ट सिर्फ कॉलम वेक्टर्स के लिए है, रिमेंबर इट, रो वेक्टर्स के लिए नहीं है. अगर आपने ये देखना है कि रो वेक्टर्स लीनियरली इंडिपेंडेंट हैं, तो फिर हम उस मैट्रिक्स का ट्रांसपोज ले लेंगे, उसको कॉलम वेक्टर्स में कन्वर्ट कर लेंगे। फिर क्या करेंगे, हम कॉलम वेक्टर्स उस वो जो ए ट्रांसपोज होगा उसको हम रिड्यूस करेंगे एचलन या रिड्यूस एचलन फॉर्म में। उसमें जो कॉलम्स लीनियर इंडिपेंडेंट होंगे उसके मुताबिक हम कह सकते हैं कि ओरिजिनल ए ट्रांसपोज के वो वेक्टर्स लीनियर इंडिपेंडेंट हैं। और फिर उनका ट्रांसपोज लेंगे तो आपके पास वही रो वेक्टर्स आ जाएंगे जिनको हमने चेक करना होगा कि वो लीनियर इंडिपेंडेंट हैं या नहीं। यस, हु इज दिस गाय? हाशिम शबीर।
सर क्विज अपेयर हो गया एलएमएस पे।
अब हो गया,
या
चले।
स्टार्ट करना।
लेट मी गिव मी 1 minute and then I'll close it.
सर क्विज पे 40 मिनट्स थे और हमें तो अभी पता लगे, तो 5 मिनट ज़ाया हो गए।
हाँ 5 मिनट है आपके यार, कोई बात नहीं।
155 पे डेडलाइन है, 115 से
तो
155 पे।
So we'll discuss this result in the next lecture. If the matrix R is in row echelon form, then the row vectors with the leading one form a basis of the row space of R, and the column vectors of with the leading ones form a basis for the column space. We'll start discussing things from this result in the next lecture. So for now, we are going to stop here because we have a quiz today. You can start your quiz.